we introduce a novel training-free approach to text-to-image synthesis as presented in the paper titled Spatial Transport Optimization for Training-Free Text-to-Image Synthesis. Text-to-image synthesis has recently excelled in high-quality image generation, particularly in a training-free manner. However, while the existing methods have been continuously focusing on several pitfalls, such as missing objects and mismattributes, another critical issue of mislocated objects remains where generated spatial positions fail to align with text prompts. What makes this problem even more significant is that Stable Diffusion consistently generates similar images regardless of spatial cues in the text, highlighting Stable Diffusion's limited spatial understanding. Our model, STORM, introduces a training-free approach that directly addresses the challenge of mislocated objects in text-to-image synthesis. By dynamically adjusting relative object positions, STORM ensures accurate spatial alignment as described in the text prompt. Now let me first show STORM's results in tackling these challenges. As shown here, STORM successfully generates images where the teddy bear is correctly placed relative to the vase, addressing the misalignment problem effectively. Beyond addressing the mislocated objects problem, STORM also demonstrates remarkable performance in resolving challenges such as missing objects and mismatched attributes. Before diving deep into our proposed method, it's essential to first understand some foundational concepts that our approach builds upon. We use Stable Diffusion, which generates images from text by integrating a clip-encoded text prompt as a conditioning vector I into the UNet model via cross-attention layers. At each time step, the attention map guides how textual token information is mapped onto spatial positions. We leverage optimal transport theory to adjust attention maps, efficiently shifting source to the target distributions while minimizing transport cost. Guided by a cost matrix, OT computes a transport plan, determining how distribution is moved between distributions. In our method, we customize the cost matrix to compute positional costs and apply OT to guide the movement of attention maps, treating them as distributions to be adjusted for alignment with our objectives. Now we provide an overview of STORM, a training-free approach to enhance spatial accuracy in T2I synthesis, addressing the misalignment of generated object positions with text prompts. We introduce the Spatial Transport Optimization framework, which leverages OT theory to dynamically adjust attention maps during the denoising process, with a customized spatial transport cost to guide positioning and prevent overlaps. It operates effectively during the early denoising steps, maintaining structural coherence while refining visual details in later steps. By integrating these techniques, STORM improves spatial alignment, ensuring outputs align more accurately with text prompts. Let me take you through a detailed breakdown of our method. Here, the prompt, "A car to the left of an elephant," is fed into the clip text encoder and converts into a text embedding, guiding the attention map to focus on image regions relevant to the text. Without any guidance, Stable Diffusion often fails to locate the object in the correct position. Our method provides a guiding framework to accurately position objects in alignment with the intended spatial context. We extract the attention map corresponding to the object token from the cross-attention layers. This is where STO comes in. Attention maps from the denoising process pass through the STO framework. The attention map, which requires adjustment, is the source distribution. Since the prompt specifies a horizontal relationship, in this case, to the left, the adjustment primarily focuses on the object's horizontal centroid position. If the prompt were to specify a vertical relationship, like above or below, we would instead adjust the vertical centroid positions, like this, while leaving the horizontal centroids unchanged. For the reference distribution, it acts as a guiding point for defining the target distribution. Typically, the source distribution adjusts its position relative to a reference point, which serves as the basis for alignment. Here, the elephant acts as the reference point for the car. Using the reference point, we can define the target distribution. The source distribution is then guided to move intelligently toward the target distribution. In this process, a custom cost function is employed, which can be represented mathematically as follows. Let's denote the value of the reference point as jref, and the current point we are computing as ij. The directional positioning delta is determined based on the relative location of ij with respect to the reference point. For example, if ij is to the left of jtextref, the delta value for the left arrow is computed. Conversely, If it is on the right, the delta value for the right arrow is computed. These arrows are then assigned differently depending on whether the direction is the desired or the restricted for the source distribution's movement. Taking this example, since the car needs to move left, the left arrow represents the desired direction and the right arrow the restricted direction. The directional computation for all directions is expressed in the equations below. Preventing overlap is crucial during movement, so we incorporate the relative attention map, A, into the cost function to address this challenge effectively. Below, we have provided example cost functions for two scenarios. We apply the Sinkhorn algorithm in our method to compute the optimal transport plan by iteratively adjusting the attention map distributions, leveraging its computational efficiency and differentiability for high-dimensional data. We optimize and update the latent vector by computing the transport loss from the STO and iteratively refining the attention maps to align with the desired spatial relationships at each denoising time step. When looking at our result, we can see that the car and the elephant are well aligned. Here's an example of the transport in the attention map. For the real attention map, we compare stable diffusion and our cross-attention map during the denoising steps. Given the prompt, a red bird to the right of a green plant, stable diffusion struggles to distinctly capture the spatial relationship between the bird and the plant, while our model effectively aligns the objects according to the specified spatial cue. Here, our quantitative results demonstrate significant improvements in spatial alignment, object accuracy, and attribute consistency. We evaluate our method using the visor, which quantifies a model's ability to accurately capture spatial relationships between objects as described in the text prompt, demonstrating reliable spatial alignment across prompts and seeds. We also evaluate our method using T2I Comp Bench, which assesses spatial relationships and attribute alignment, providing a holistic evaluation of text-to-image synthesis performance. Our score shows that the generated images position the specified objects correctly and accurately reflect the given attributes. Our model achieves significant enhancements in the user study, with spatial correctness showing a particularly remarkable increase. We conducted ablation experiments on our STO framework by comparing its application from late steps to early steps, revealing that applying it in the early steps is most effective for resolving spatial misalignment issues. To conclude, STORM redefines training-free text-to-image synthesis by addressing spatial misalignment, setting new benchmarks for spatial control and adaptability.